Hello, I'm Ji-yoon Kim, and I'm a co-moderator of the 6th GSI International Forum. Today's forum is titled Quantum Technology, the Next Game Changer, and is jointly hosted by KAIST GSI and KTV. We're going to be joined by the really famous and world-renowned scientists and the business leaders, and the main event will start at 9 a.m. And until then, we're going to have a warm-up session with a light conversation, and we're going to learn more about the quantum technology and how it will change our lives in the future. You know, sometimes the backstage scene is much more fun than the main event, so please stay tuned. We are joined by 6 guests here today, this morning, and it's really a pleasure to meet you all. Could you please take a moment to introduce yourselves and in the way that you like to be described by other people? So can you start with Director Son-hoon?
Hi, this is Hoon Son. I'm the director of KAIST Global Strategy Institute, which organized today's forum. My staff members, including myself, had many sleepless nights preparing for this forum. And I'm crossing my fingers, hoping that today's event goes well and all of us can have good night's sleep today. Thank you.
Well, nice work, Director Son. Professor Kim Jae-hwan.
Yes. Hi, my name is Jae-won Kim. I'm a professor and the vice president of Korea Institute for Advanced Study in Seoul. Here I have a Korean national flag, and what you see at the four corners, they are made of solid bars and dashed bars, and they are actually bits. Solid bars are ones, and dashed bars are zeros. Now, what do you see in the center of a national flag? That is, what does it look like? Alphabet Q. And that I would say that is a qubit, quantum bit. And we are going to talk about qubits a lot today.
Well, I never thought that way. All right, Professor Andreas Heinrich.
Good morning. So my name is Andreas Heinrich, and I'm the director of the Institute for Basic Science, the Center for Quantum Nanoscience at Ewha Women's University. And let me start with 2 fun facts that you may not guess about me. First of all, while I may not look Korean, I really feel Korean. And I've been here for 6 years working nonstop here in Korea. And the second fact that you may not guess is that I actually created the world's smallest movie. And maybe we'll have a chance to talk about this a little bit later. Now, even though I work in this field of quantum science, I am really looking forward to learning even more about quantum science in this forum today. Thank you.
Thank you. And Professor Lee Jung-gu.
Hi, I'm Jun Kyuri, also known as Kevin. I'm a professor at electrical engineering from KAIST. I just returned from an overseas trip to meet 8 leaders in quantum computing research and development in the US and Canada. I had to squeeze this schedule to 1 week, which was originally 2 weeks, in order to attend the exciting global forum today. By the way, I have founded the first university research center on quantum computing in Korea, and also, which is called QCAI, and the first quantum venture in Korea, which is called QNOVA Computing. Thank you.
Well, I'd like to hear more about your company later, maybe. Yeah. So, Professor Son Young-ik.
Hi, I'm Young-ik Son, a faculty from School of Electrical Engineering at KAIST. When you watch a movie, Back to the Future or the sitcom Big Bang Theory, you see those crazy, nerdy mad scientists. I'm like those people in real life. Thank you. Nice to meet you.
Well, thank you. Nice to meet you too. And we have very special guest here, Joel. It's quite a surprise.
Yes. Hello, everybody. My name is Joel, and I am a broadcaster, model, and actor in South Korea. I actually majored in political science, much like yourself.
Good.
Yes, and today's topic is definitely a very complex and deep one, and I think that it is probably important and good for myself to be here to kind of represent the general audience and the general public and maybe ask some questions to our esteemed guests so that maybe it's a little bit easier for them to understand. So hope everybody stays tuned.
Well, that sounds more comforting to me. So I'm not the only one here who has no idea about the quantum technology. Okay, so let's get into the actual topic of today, so quantum technology. Well, this is such a buzzword recently, but as a matter of fact, I don't really know much about that. And I believe a lot of audience feel the same way. So could you please explain us briefly? So I'd like to give you one sentence like quantum technology is something like in blank. So you have to fill out that blank. So is there any volunteer to fill out the blank first? Yes?
Maybe let me start and try to answer this very difficult question.
Okay.
So quantum technology is based on quantum mechanics, and that is the description of the world that describes essentially everything. The atoms, the molecules, this table, everything that we're made of is described by quantum mechanics.
You lost me already.
But it is time now to take this more theoretical approach of quantum mechanics and basically engineer the quantum future. So that's where we're at.
I see. Well, any volunteer who can
Oh,
explain?
I can do
Yes.
some. Okay. So quantum is the collection of wisdom of the greatest minds in physics. So that means this is the principle that governs nature, and that is realized by the experiences of the geniuses in physics. That's probably what it is.
Okay. Is there any more intuitive way to explain it, like a fill the blank?
Let me give it a try.
Okay.
I want to say quantum technology is Apollo 11. Apollo 11 is a spaceship that took humans from the Earth and let them put their feet on the moon for the first time in human life. So that was such a historical moment that let us meet the completely new world. I think quantum technology is similar. Of course, it's not going to be as tangible as landing on the moon, but I'm sure it's going to let us meet the new world we've never been to.
Okay. Well, I remember it was the biggest leap for the humankind. Professor Kim, your turn.
Okay, this is my turn. And in one sentence,
Okay.
quantum technology is the ultimate technology, since the principle of the nature is quantum physics. So we have to talk about the quantum bits or qubits over beyond the bits in digital information.
Okay. Joel, did you get it?
All right, so I'm going to be honest. I'm not totally understanding everything right now, but it does sound very, very important. There is a certain name that I wanted to bring up and a quote that I actually know by Dr. Richard Feynman, who is a famed theoretical physicist and the winner of the Nobel Prize. Very, very good stuff. Yes, he is credited as being the first person to coin the term quantum computing. And he once said, nobody really understands quantum mechanics. So that should tell you how difficult it is to understand. But it is, I feel like, a field that needs to be focused on in the future, especially going forward. And I definitely hope that I can learn a lot and our viewers can learn a lot about quantum mechanics and physics and everything this time. So everybody stay tuned with me.
Great. Well, it's a little bit encouraging
Oh,
and
yes.
comforting as well that even the smartest guy in the world could not really explain it in the brick words. That's great. So we'd like to hear more about from our guests here how they got into this field, quantum technology. So, Professor Kim, I heard you've been working on this field since 1990s.
Yes.
It's quite a long time.
Right.
Yeah.
Yeah. I studied quantum chaos as a graduate student after getting PhD. While I was working for Samsung in 1990s, I learned to know how to use quantum mechanics for secure communication and computation. And I presented the quantum ideas for information technology in front of Samsung executives. After my presentation, the first question was so disappointing. What is quantum? So an hour of seminar was not enough to overcome the mystery of quantum mechanics. And then I had a chance to work with on quantum information science at KAIST for 2 years. And my wife gave me a big okay to go. And I gave up good pay and secure future at Samsung. And I had to leave my 3 little kids to my wife during the weekdays and with much reduced income. And the future was as uncertain in those days as quantum physics and at that time. Yeah.
And now you're happy.
Yes, I'm very happy
And
to study the mysteries of quantum physics and the application of quantum information science.
yeah, and I'm sure your wife is as happy as you are.
Yes, yes.
All right. From your assessment, where Korea actually stands in terms of quantum technology?
Okay. Quantum information science did not get much attention for the first 10 or 15 years in Korea. Some of the first achievements were done by Korean scholars, but not many enough to wake up Korea at that time. Some brilliant and highly dedicated Koreans could not get good positions and left the field. Now we do not have enough experts because of that to push the quantum technology forward. But we have many young students and young PhDs are coming into this field, and the funding situation is getting much better. And many stakeholders are showing their interest in quantum information science, and Korean quantum future is not uncertain anymore.
Great. It's good to hear that it is becoming more promising. Professor Jung-gu Lee, I heard you're actually the first one who started the startup company, the quantum technology in Korea. So could you please introduce your company and what it's doing and what is the research?
Right. This is a great opportunity for me to introduce my companies. So quantum computing is the dream technology that will change the world, probably. But there are several fundamental issues that we have to resolve. The quantum computing in the near future may even have errors in the results. And we have to fix that problem. So my company is developing software solutions that can fix such kind of problems that can be better than supercomputer. So in using this platform, I'm going to introduce the material and drug design solutions to the market, which will lead to the great advantages in quantum applications. So I hope this one can be a very interesting adventure for me, and I think we will see the great future of these efforts.
Great. The one thing that always come up to my mind is those top-notch high-tech companies and academia, all the technologies, that's great. But when is going to be available to the people like me?
Well, so first of all, we have to have the quantum computer to see the great advantage, right? According to the leaders in this industry, such as IBM and INQ, their roadmap suggests that such kind of quantum computers will be available in 3 to 4 years. It's very close in near future. So once that is introduced in the market, I think the market will grow very rapidly, and also the value of the quantum softwares will be also highly appreciated. I think that's the time we can start the quantum business in the world.
So it's going to take place in my lifetime.
Oh, sure, yeah.
That sounds good. Okay, now let's hear from Director Andreas Heinrich from the IBS Center for Quantum Nanoscience. You have worked for IBM Research in Almaden in the United States for around 20 years. Am I right?
Yes, that's correct. So I came to Korea about 6 years ago to start this Center for Quantum Nanoscience. And as that name says, it combines quantum science and nanoscience, so two fairly advanced topics. Now, what do I actually do on a daily basis, right? So we have tools that allow us to work with individual atoms, and those are the basic building blocks that quantum mechanics was developed for to describe these atoms, right? And we have tools that allow us to look at individual atoms on surfaces. We can see them. We can not only see them, we can also move them. We can put them next to each other, let them talk to each other. And over the last few years, we've also gotten very interested in harnessing the quantum behavior, making superposition and entanglement of these atoms. So we are on our way to make qubits. But I'm really a basic science kind of guy. I don't try to make quantum computers. I try to understand the basic mechanisms that underlie these qubits.
I see. But I also find a really interesting part in your CV. So you're a film director. actually. And actually, your film was listed in the Guinness Book of World Records, and you won the Gold Lion Award in the Cannes. Is that right?
Yes, that was when I was still working at IBM, so almost 10 years ago now. I was approached by IBM Marketing whether we could highlight IBM's power in nanotechnology on the atomic scale by making a movie. And you can see a few frames here. Every one of these dots here is a single atom. And so this shows you the power that we have with our tools to move these atoms and to put them next to each other. And so you can see here a frame that contains about 150 individual atoms that we placed there on purpose. And there's about 250 frames. So you can imagine it was a lot of work. It took about 10 days straight, working with 4 people, literally 24 hours a day.
Wow.
And to make this movie was sort of a 1-year overall project. And why would you take that much work and effort to do this as a scientist, right? I believe strongly that we need to also reach out to the general public. And
Right.
here we're doing this by telling an emotional story. This boy is falling in love and dancing with this atom, and they are just communicating with each other. But if you look a little bit deeper in there, then you can see, oh, these are made of atoms, and you can get drawn into the world of atomic scale and quantum. And so I invite you all to look at this on YouTube. It's available on YouTube with a lot of basic scientific information on how this was made.
Well, this is one of the most productive things from this academia. Well, I'll make sure to watch the one on
Please do.
YouTube. All right. So next interview, actually, the mic goes to the Professor Young Son. So you were trained at Harvard University, and also you worked at the Psi Quantum. Is that right?
That's right.
And that is the company received a huge amount of investment from Microsoft. Huge investment. Yeah. So how was the experience there, and what did you do the research?
So the research I'm doing right now is to build a quantum computer based on light. And this light is the same light you are thinking of right now. So it's the light you are experiencing every day, interacting with. And for example, you are seeing me right now using the light. So it's that light. But probably you've never thought about if light can be quantum. But in fact, light is also quantum. So for example, if you think about the matter, right, it's a little bit easier to understand. The matter, if you slice it into small pieces, it's going to become an atom. And it's pretty well known that atom is described by quantum mechanics. And light is the same. If you slice the light into smaller pieces, in the end, you will meet this particle of light that's not breakable. That's called a photon. And I'm using this photon to build a quantum computer. But it turns out that it's very hard to control this photon. So I'm trying to use this technology called silicon photonics. And this silicon, the word, might be familiar to many people because this is the same silicon, the semiconductor, used for building computer chips. The difference is that for computer chips, these silicons are made in a way that they control electrons, and these electrons are used to process classical information. However, the way I do is to tailor this silicon, and silicon will control the photon, and photon will be used to process quantum information.
Okay, a lot of scientific jargons. Joel, you're with us, right?
I'm trying to follow along.
Okay,
Try.
great. So this is the question I have to ask you. So when this technology comes arrive, and how will it change our lives?
So I think that's one of the hardest questions to answer in our field. So let me try my best. So I think it's very hard to predict the specific details what's going to happen in the future, but I think I can say a few by looking looking back the history, what happened when digital computer was born. Back in 1960s and 70s, transistor was born, and people were trying very hard to make the computer chips. And at the time, I'm pretty sure no one could imagine that what we have right now, we have smartphones in our hand. So I think it's very similar to quantum technology because quantum technology is just about to begin. So it's a beginning phase, so it's hard to imagine what's going to happen in 10, 20, 30 years later. But I think I can say a few things about what we're going to have. So first of all, this change the quantum technology will bring us is not going to happen one day. It will happen bit by bit, day by day. The change probably you'll feel small, but the accumulated change of over 10, 20 years, it's gonna be big, and I'm pretty sure it's gonna be as big as the innovation brought by digital computer, or it can be more.
Well, wait a minute. Professor Lee actually said it's going to take us just 3 or 4 years.
Well, I think the change happening in 3 years, 10 years, 20 years, that's gonna be all different levels, I think.
Okay.
So I think there is some different metrics. So what he's talking was an error-free quantum computer. What I was talking is the quantum computer that can be better than supercomputer. So the timelines are different. Yeah.
Okay, I see. So timelines are different. All right. So we have very special person up there, the director Son Hoon, and you are the one who arranged all this forum and make it very memorable and important one. So I was wondering why and how did you come up with the idea that quantum technology should be the topic of this year?
Yes, we have been doing research for quite some time, and we predict that many emerging technologies such as artificial intelligence, metaverse, Web 3.0, blockchain, all these technologies will demand huge computational power and speed. And I believe that quantum technology, especially quantum computing, can address this issue and truly transform our way of living. And also personally, I have a strong interest in investing companies relevant to quantum technology. And for example, I've been following the stock price of IonQ, which is the company that we will be discussing today. So that's why and how we came up with this topic.
Well, Professor Lee also have the company of his own, and you're not investing his company.
His company is not publicly available at this
Okay,
point.
so
I will love to invest in his company as
So-
well.
when are you going to thinking about the IPO?
Well, okay, so it's a company secret, but it'll come soon.
Okay, so are you willing to invest in his company then, Joe?
Let's have coffee after.
Oh, you are
Okay. All right. So, Director Son, so the Global Strategy Institute, you are director of that institute, and I'm wondering what kind of work that you guys do there, and there must be some future plans for the institute.
Yes, the Global Strategy Institute was established in 2020. It is a leading think tank representing KAIST. We provide policy and strategic advices on domestic and international matters, especially through our expertise in science and technology. And regarding your second question, we are planning 2 additional forums later this year. They are not finalized yet, but we are thinking 2 topics. One is on how we can minimize social inequality and division through science and technology. And the second one is on renewable technology. And also, you can find more information regarding these 2 forums from our website at gsi.kaist.ac.kr. And also, if you like to, you can suggest some topics for our future forums.
Well, there's something that I understand: social inequality and the division, and how the technology and science can change. Can you briefly tell us how can it change?
Well, we are thinking right now, so you have to watch the next forum to get.
Oh, I can say that. I can see how great organizer of all the events. This is already the 6th the forum, right?
Yes.
And the institute was established in 2020, but
That's
you
right.
already have 6th forum, and you are planning to have another 2 more this year.
Absolutely, yes, that's correct.
That sounds great. Well, I look forward to GSI's future, and I believe you guys have much more to come and all the innovations in science and technology. Okay, so the main event of the 6th GSI and International Forum will start at 9 a.m. And I very much look forward to it. And Joel,
Yes.
so would you like to briefly introduce about the forum?
Absolutely. Okay, so the topic of the 6th GSI-IF is quantum technology, the next game changer. To help the audience better understand the subject, we are going to be looking at different types of quantum technologies that have been featured in movies. So, in the first session, Director Jerry M. Chow of Quantum Hardware Development at IBM will present a talk on the opportunities and challenges of quantum computing as innovative growth engines. The second session will feature a keynote speech by Professor John Preskill of Caltech, who is a global authority on theoretical physics. We have also prepared a bridge video titled Quantum in Art. The third session will be led by Professor Jung-san Kim of Duke University, who is also the founder and chief technology officer of IonQ that we mentioned earlier. He will present on the insights of emerging quantum startups. So everybody, please stay tuned to our forum. It will be a great opportunity, myself included, to learn from the world's greatest leading experts in quantum technology.
Well, thank you, Joel. It was an excellent introduction. The main event will be taking place soon at 9 a.m. And you can watch live via the official YouTube channels of KTV or KAIST. And also you can watch it on TV, on KTV channel. The 6th GSI International Forum will feature the speeches by some of the well-known and the world's most prominent experts in quantum technology. And we are going to talk about the dream computer that will bring about the changes in our life in the future. So quantum technology, the next game changer, it will help viewers to understand why the future is heading toward the quantum technology and why it's so important. So please stay tuned in the forum with us, and we'll be back in a minute. 요거 끝나고 바로 그 메인 이벤트 들어가는 거죠?
Why are scientists in sci-fi movies always oddballs or lunatics? Time machines, teleportation, AIs, everything they create just can't be explained, just can't be understood. But there's a cheat code that will solve this issue, the quantum. Now listen up and be careful not to misconstrue. After all, we're talking fiction, not fact. The important part is that natural disasters, divine games, superpowers, and other such imagined phenomena in movies have begun to be explained with quantum mechanics. From now on, when you watch a movie, just remember 2 things. The key features of quantum mechanics, superposition, and entanglement. By putting the past, the present, and the future in superposition, people can travel through time. By putting multiple universes such as solar systems in superposition, a worldview based around a multiverse becomes possible. If the universes in superposition begin to engage in quantum entanglement, perhaps parallel universes and alternate selves may be discovered. If quantum entanglement is hastened and improved, would the instantaneous teleportation of information also grow feasible? On top of all that, Quantum computers that utilize superposition and entanglement in other ways also bring the notion of virtual reality closer to us. But please consider the following. Is all of this really only possible within the realm of imagination? You'd be surprised at just how much of what Back to the Future imagined became true by now. The quantum is now by our side wherever and whenever. What you once believed was mere fantasy will become opportunities of the future. And it's all thanks to the quantum. Quantum mechanics. Facts in film become reality.
Hello, I'm Ji-Yoon Kim, and one of the co-hosts of the 6th KAIST GSI International Forum.
Hello, everyone. I'm Jae-won Kim, co-moderator for today's forum. I would like to start by welcoming everyone tuning in via YouTube and KTV.
Well, since hosting its first international forum back in April 2020, KAIST GSI has successfully hosted 5 forums discussing global issues and the key drivers enabling scientific innovations and the development of the next generation technologies.
This is the 6th GSI forum presented by the Global Strategy Institute of KAIST. The topic of today's forum is quantum technology, next game changer, ? We are going to hear from the world-renowned scholars and experts about the present status and future of quantum information technology.
So we'll begin the forum with the welcoming remarks by KAIST President Kwang-hyung Lee. As a computer scientist and futurist himself, and President Lee has always placed a really big emphasis on quantum computing as an important technology, and it will lead our country's future and the growth. So without further ado, please welcome President Lee with warm applause.
Hello everyone, it is my great pleasure to welcome you all. It is said the future is quantum, and the future is already on its way. The quantum revolution is unfolding now, exploring the enormous advancements in our various industrial sectors from ICT and manufacturing to healthcare and finance. KAIST opened the nation's first AI and quantum computing information technology research center in 2018 in collaboration with the Korean universities and corporations for R&D, and we are doubling down on disruptive innovations. I believe this forum will navigate how quantum technology will benefit our new world as a game changer. I look forward to the deep insights and new knowledge discussed during the forum, inspiring us to explore new visions and strategies in the age of Pax Technica. Thank you very much.
Well, thank you so much for your continuing support for the forum, President Lee. Quantum information technology is probably the hottest topic recent days, but it's not really the easiest one to understand. So in order to help our viewers what the quantum technology is, we prepared a short video clip that can show you and explain kindly about the quantum technology. So please take a look.
This is an academic discipline that started with the question: what are the building blocks of nature? Quantum mechanics. Quantum mechanics is a fundamental theory in modern physics that explains the material world at the microscopic scale of atoms and electrons. In the early 20th century, physicists developed a radically new theory of nature: quantum mechanics. Quantum mechanics was a new academic discipline developed by young physicists such as Niels Bohr, Werner Heisenberg, and Erwin Schrödinger. One of the core principles of quantum mechanics is wave-particle duality, a concept which states that light and matter have the properties of both waves and particles. It was difficult at first for scientists to intuitively understand that particles can behave like waves. If we shoot particles through two slits, they will go through those directly, leaving marks on only two places. Waves, on the other hand, will show a more intricate interference pattern. Surprisingly, it was experimentally verified that particles also exhibit wave-like interference patterns, confirming the wave-particle duality. Therefore, all matter has the property of waves and particles at the same time. Just as waves can interfere with each other, particles can also be in superposition. However, quantum superposition is not like mere wave superposition, but the superposition of all states. That is, the particles in question can be in multiple states at the same time. Already in the 20th century, quantum mechanics played an important role in many industrial developments familiar to us. A recently emerging new application of quantum mechanics is the quantum computer. The idea behind the quantum computer traces back to Richard Feynman and Yuri Manin in the 1980s. Back then, the quantum computer was a mere academic curiosity. That changed in 1994 when Peter Shor discovered his famous factoring algorithm. Quantum computers can speed up certain computations exponentially by harnessing the power of quantum mechanics. Classical computers consist of bits, each of which can be 0 or 1. But quantum computers consist of qubits, which can be both 0 and 1 in many different ways because the qubit is represented as a superposition of 0 and 1. And interestingly, any two qubits can be entangled with each other. Two key features, superposition and entanglement, can be utilized in quantum computers, which leads to sped-up computations. As the performance of quantum computers improves, it is expected that they will bring innovations in areas of science and technology intimately related with daily life, such as the development of new and better fertilizers, batteries, and potentially other industrially relevant materials. This is possible because quantum computers are good at simulating quantum mechanical systems and precisely analyzing and predicting quantum mechanical phenomena. As Richard Feynman said, "Nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical."
Okay, now let's begin the first session. In the first session, we're going to discuss the opportunities and challenges of quantum technology and quantum computing as innovative growth engines. And we're going to have Dr. Jerry Chow as the first keynote speaker. Dr. Chow is the director of quantum hardware development at IBM, and he specializes in quantum error correction and quantum machine learning. In 2012, Forbes magazine nominated Dr. Chow as one of the 30 under 30 list in science. Currently, he serves as a co-chair of Global Future Council on Quantum Computing, and he's also a fellow of the American Physics Society. So please welcome Dr. Chow.
Great, thank you very much for inviting me to speak at this really wonderful event today. And what I want to do is talk a little bit about what it takes to really drive growth with quantum computing. And there's been a number of really exciting discussions and introductions to quantum and quantum mechanics and what's behind all that. But I actually want to take a slightly different lens, and which is really to talk about where this area is going and the real potential that we have for how this is going to be a tremendous tool for computation moving forward. Now, from IBM's perspective, we've been in the game of quantum information and quantum computing for many decades, right? Dating back to the initial ideas behind quantum information theory with Charlie Bennett in the late 70s to being involved with some of those early thoughts with Richard Feynman, right? That was discussed previously. But I would say that the modern day kind of evolution of excitement where we are with quantum computing really stems from a demonstration that we had in May of 2016, which was when we placed the first superconducting quantum computer on the cloud. It was a 5-qubit system, and it was accessible from anywhere in the world. And it's driven a lot of the ecosystem growth and the interest throughout industry, academia, and governments throughout the world in these last few 6 years or so. And so subsequent to that first launch of a 5-qubit processor, we actually built up an actual system, right? And one that is actually deployed, that is capable of running actual client workloads, and in fact, completely contained within an environment that doesn't require a research setting anymore, right? So taking it outside of those laboratory settings, but into one which is fully deployable anywhere in the world as this quantum system one. And we've seen tremendous amounts of growth, right, already. Just in these last few years, where we've turned quantum computing into a reality in terms of accelerating adoption and accelerating usage. Today, we host over 20 operational systems. We have over 400,000 users. We have over 170 plus network members of our business ecosystem called the IBM Quantum Network. And an interesting thing here is that in terms of running actual circuits on real quantum computers, we're seeing about 3.5 billion of those executions daily. And so this pace is really a piece of the growth throughout the ecosystem in terms of those that use it, but also partners that can work with us to explore how quantum computing is going to make a difference for their businesses. So amongst those 170 plus members working with us, this includes a number of industry clients, including Fortune 100 companies, those at a national scale in terms of partnerships and driving education in many different through different hub interactions and serving the quantum service further to their local ecosystems. But truly, we're seeing this sort of exponential growth of adoption, right? So just kind of, I like to show this graph because it dates back to around 2016, and we just see this exponential increase in the total amount of executions cumulatively across all of our quantum systems. And today, our largest system that we actually have available on the cloud is 127 qubits. It was deployed back in late fall last year, IBM Washington. It's from our Eagle family of processors. And this is just one of a number of 20 plus quantum computing systems online with varying metrics in terms of the number of qubits, in terms of the achievable quality metric, which we measure called quantum volume, and as well as the speed metric in terms of how fast can you actually operate algorithms on these devices and circuits on these devices. And so that's the reality, which is that we are building this ecosystem grounded upon real systems that are available and accessible, and driving a lot of learning, driving a lot of applications development. And the really big part of that is that we know that there are really tremendous opportunities in quantum computing, and it's going to take running on quantum hardware to be able to realize it. But also what's interesting is to then categorize what are those areas that we do expect to see development and advantage using quantum computers over using traditional high-performance classical computers. And it's actually nice to group this into three main categories. There's simulating nature, and I think the previous little primer video on quantum talked about this, but in terms of simulating nature and understanding chemistry better to design better batteries, to understand materials better for corrosion, improving catalysts for an enzyme design, right? So these are really tremendous societal goals, right, that has potential impact using quantum computing. And then there's another category which we could call data with structure. And this really hints at a lot of potential application in the machine learning space. Classification of data with really rich and unknown structure. Things like ranking, fraud detection. And then there's there's a third category of problems which we would call non-exponential speedups, but also potential avenues of impact, including optimization, portfolio optimization, energy grid network optimization. And so all these all these areas are looking at long-term goals that we can drive economic value and really make a societal impact using quantum computing. And the opportunity here, right, and the room for growth is tremendous throughout industry, right? This is an independent analysis performed by Boston Consulting Group that breaks this down in terms of those three critical areas. And what is the opportunity for the market at the maturity of the quantum systems when we actually have fully fault-tolerant quantum computing? What are we going to be able to see in terms of market opportunity? And it's really in the hundreds of billions in each one of these potential categories. But how do we get there, right? And how do we accelerate the path to really getting to that growth, right? And so there's certainly the part in terms of where we see is in terms of improving the underlying hardware and driving a lot of that. But that fits within a four-pillared approach that we see, right? So there's certainly the idea of providing the best-in-class quantum and classical computers together, right, as a tool and as a resource, and that's the services and infrastructure piece. But hand in hand with that is driving innovation that to bring innovation to drive economic growth, right? There's a lot of R&D throughout the world ecosystem that we need to further transform into become quantum ready, that will accelerate the advancement. And along with that is really driving workforce and enablement, right? How can we get quantum research and quantum industry together so that there's a larger number of people who can actually enter this really booming workforce in the future? And then altogether, this also hinges upon further R&D, like new research, new ideas, new development to keep building the new foundational tools that will help us solve the real world problems of interest on these quantum systems as they further mature. And so one real important piece of this that we see at IBM has been to grow partnerships to drive regional quantum ecosystems, all right? And so we certainly have our quantum data center in New York, which houses now 24 quantum systems. In the past year, even during the pandemic, we were able to place a quantum system, one out in Germany with the Fraunhofer Institute, and also one in Japan with the University of Tokyo. And we're excited to be driving more of these partnerships, including in the United States with Cleveland Clinic, and then also with Korea, South Korea, with Yonsei University, with a projected target date of in 2023 for a system there. And then most recently, we announced a partnership with Quebec for a system in Bromont, Canada. And each one of these, we've already started to see the ones that have been deployed, tremendous growth and driving industrial engagement and research using the systems both in the Fraunhofer case as well as the University of Tokyo. And we really expect to see a similar amount of growth as we drive these next few systems, as we can imagine what the quantum data center of the future looks like. Thank you.
Dr. Jerry Cho gave a very exciting news on IBM quantum computers. And actually, many KAIST students are already using IBM quantum computers, and they are competing on IBM quantum hackathons too. Now, we are going to have a short question and answer session with Jerry Cho.
Can I go for
Yes,
the question?
please.
Okay, so I really thank IBM to bring the quantum computing to the world. Actually, IBM is one of the leaders in this area. IBM also just introduced the Eagle QPU with 128 qubit and 127 qubits, but the quantum volume-wise, it needs some improvements from there, right? So and also there will be, soon there will be you are introducing 1,134 qubit QPUs in the near future. And I'm just wondering if you can have also improve the quantum volume of these QPUs, so you can be a real useful quantum hardware in the near future. Is there any hurdle for that? Yeah,
absolutely. This is a great question there, and I think a big part of the what I would say there is that what we are driving is not just individual devices, right? But in fact, a roadmap of devices, right? So Eagle was the next step in our scaling roadmap. Right? We went from 27 qubits to 65 qubits to 127. We have Osprey with 400 plus, and then Condor, like you mentioned, at 1,000 plus, coming this year and then the next year. And those allow us to drive specific technologies in the realm of scaling these devices. At the same time, we continue to drive improvements in order to make quality better, pushing quantum volume, and for that matter, improving the underlying qubits. Just last week, we actually announced that we were able to hit quantum volume of 256. That was on a 27 qubit device on a Falcon processor. But all these things kind of happen in parallel. And so what I like to refer to this is really agile hardware development. As you might know, in the semiconductor industry, we have all these different technology nodes, one generation after the other. And what we're actually doing at IBM is a lot of agile hardware development, of having many of these different layers of new devices happening in parallel. And we're feeding off of one another, but they also have different cycles of learning. And so whereas we are driving some elements in scale, we're also driving other elements to improve quantum volume. And then those feed into the next generations of the scaled upwards. And so those all come together in order to really drive forward our full roadmap to provide more useful systems to the ecosystem to play with. And for that matter, even with the quantum volumes that we have with the Eagle processor, it is already of a size, and using other noise mitigation techniques, a system worthy of looking at certain kinds of potential quantum advantage demonstrations.
Joel, you seem to be very curious.
Yes.
Would you have some question?
Yes, I do actually. First of all, thank you, Director Cho, for taking my question. I am wondering, what industry sector do you see to be the most active to introduce quantum computing applications?
Yeah, so that's a really good question too, right? I think that there's one of the areas I think that often is talked about is there's tremendous potential for materials development, right? So there's just, in terms of just simulating nature, understanding how to improve underlying molecular structure is kind of at the heart of what Feynman said that quantum computers might do. And certainly, I think one of the real areas where we know that classical computing is limited, right? Even the best high-performance computing you have today is limited in terms of what you can potentially simulate or study with certain kinds of materials. And this is where quantum computing has a real potential advantage.
Now, this concludes question and answer with Dr. Jerry Cho. Thank you so much.
You're welcome.
Well, thank you, Dr. Cho. And we're going to open the second session with the keynote speaker, who is a leading scholar in physics. And he's also very well recognized worldwide for his academic achievement. So let's meet our next speaker.
It is a great honor to introduce Professor John Preskill. John is Sir Richard P. Feynman Professor of Physics at Caltech and currently the Director of the Institute of Quantum Information and Matter. John is a theoretical physicist and started off his career as a particle physicist. But in the 1990s, John switched his research direction, mainly spurred by the discovery of Shor's quantum algorithm for factoring integers, and started to make important contributions to the field of quantum computation and information. In particular, he produced many fundamental works on the theory of fault-tolerant quantum computation, which is a study on how to make a noisy quantum computer effectively noise-free. In more recent years, John coined several key words used in the field of quantum computation, such as quantum supremacy and near-term intermediate-scale quantum devices, also known as NISQ for short. Lately, these words have played an important role in defining the key questions that our field as a whole is attempting to resolve. As such, I think we will get to hear John's insightful view on where our field currently is and where we are heading to. Okay, John, take it away.
We'll connect Professor John Preskill. Hello,
Sorry.
Professor.
Hi,
Hello. Well, thank you for joining us today.
glad to be here. Thank you very much, Isaac, for the very kind introduction, and thank you all for the opportunity to speak here. We can anticipate that in the future, quantum computing will bestow substantial benefit on humankind. And that belief rests largely on two central ideas: quantum complexity, which is our basis for thinking that quantum computers will be powerful, and quantum error correction, our basis for thinking we can scale up quantum computers to large systems that can solve very hard problems. When we speak of quantum complexity, what we have in mind is the extravagant complexity of describing with ordinary conventional bits the information content of a system of many particles. For a system with just a few hundred qubits to give a complete description of its properties in terms of ordinary bits would require more bits than the number of atoms in the visible universe. Now, that in itself doesn't mean that quantum computers can do things that we'll find useful, but we do have two reasons for thinking that quantum computing will be powerful, a few reasons. One is that we know of problems which are believed to be hard for conventional computers, which theoretically quantum computers will be able to solve efficiently. Finding the prime factors of large numbers is the best known example. And theoretical computer scientists have given us arguments why, if we do a modest size computation and then measure all the qubits, we'll be sampling from a probability distribution, which is hard to sample from by any efficient classical means. But perhaps most tellingly, we don't know how to simulate in general what a quantum computer does efficiently with an ordinary computer. And that's not for lack of trying. Physicists and computer scientists have been working for decades to develop better methods for simulating complex states of matter. And still, in the hardest instances, the best algorithms that we have on an ordinary computer have a runtime which rises exponentially with the size of the system to be simulated. So we believe that there are problems which are too hard in practice to solve with conventional computers, but can be easily solved with the quantum computers of the future. And it's a compelling question: what are these problems that are feasible quantumly and not classically? And we've learned a lot about that over the past 25 years. I think there's a lot more to learn about that. But if you're a physicist, there's a natural place to look for such problems, because we expect that with a quantum computer, we'd be able to efficiently simulate any process that occurs in nature. And we don't think that's true of conventional computers, which can't efficiently simulate very highly entangled matter. So with a quantum computer, we ought to be able to go further in exploring the properties of complex molecules and exotic materials, and also explore fundamental physics in unprecedented ways. But the idea of building a quantum computer is now over 40 years old, and we're just now getting to the point where quantum computers are capable of doing interesting things. So evidently, quantum computing is hard to do. What makes it hard is that in a quantum computer, we want to simultaneously satisfy a set of criteria that are nearly incompatible with one another. We want our qubits to interact strongly with one another so we can rapidly process the information that they encode. But we don't want the qubits to interact with the outside world, which would cause a quantum computation to fail. But we do want to be able to control the quantum computer from outside and eventually to measure all the qubits to read out a final result. And it's very hard to build a platform that satisfies all of these desiderata. So it's actually taken decades of advances in materials and qubit design and control to come as far as we have. There are a number of different approaches to building quantum hardware which are under development and advancing steadily. And it's important at this stage to continue to pursue these different hardware paths in parallel, because we really don't have a clear understanding yet of what technology has the best long-term prospects for scaling up to large systems. And it may be a hybrid of different technologies, which turns out to have special advantages. The formidable enemy of the quantum computer is what we call decoherence. Quantum systems have the inconvenient property that you can't observe a quantum state without disturbing it in some uncontrollable way. And what that means is that if we're going to process quantum information, we need to keep it almost perfectly isolated from the outside world. There can't be any leakage of information from the computer to its environment. And that's hard to achieve because our hardware is never going to be perfect. But we've understood in principle that there's a software solution to this problem based on what we call quantum error correction. And the essential idea is that if we want to protect quantum information from error, then we should encode it in a highly non-local fashion, shared by many qubits distributed throughout our device. And then when the environment interacts with the parts of the computer one at a time, it can't perceive the encoded information, and therefore it doesn't damage it. And we've also understood how to efficiently process information that's encoded in this very non-local, highly entangled form. So where's the technology now? Arguably, we've reached the advent of what has been called the NISQ era, NISQ for Noisy Intermediate Scale Quantum. We say intermediate scale to emphasize that we now have devices with 50 or more qubits, such that we can't, by brute force, simulate what the quantum computer does with the most powerful existing conventional computers. But noisy reminds us that these are not error-corrected devices, and so the noise places a severe limitation on their computational power for the time being. Now, for physicists, NISQ is quite exciting. It's providing us with a tool for exploring the behavior of highly complex matter in a regime that's never been experimentally accessible before. And it may be that NISQ has practical applications that are of broader interest, but we're not really sure about that yet. We should think of NISQ as a step towards the more powerful quantum technology that we're hoping to develop in the future. I do feel confident that quantum computing will have a transformative impact on society in the long run, but we're not sure how long it's going to take to get there. Now, somewhat optimistically, we can anticipate that with a device of just a few hundred very high quality qubits, we'd be able to run applications to chemistry and material science and optimization that surpass what we can run on our most powerful conventional computers. But the catch is that would be true if these devices operated perfectly without any errors, and that's far from the case with the current technology. So if we assume that we can do a computation on a quantum computer with a probability of error of, say, 1 part in 1,000 in each step of the computation, then we'd be able to use the idea of quantum error correction to compute robustly, but at a very hefty cost in the number of qubits we need. In order to have sufficient redundancy in the stored information to protect it against error, we might need millions of physical qubits to run these same applications. And that's a huge step beyond where we're likely to be in the next few years with, say, hundreds of physical qubits. Now, what we'd like is to have more qubits and higher quality qubits, more accurate operations acting on the qubits, and that's a big challenge. One thing that might help us make progress are advances in materials. Those require substantial investment, and the pace of progress is hard to predict. But in any case, we need more than just better materials. We need better ideas about how to use those materials to make robust and scalable qubit systems. So where is all this taking us in the long run? Nobody really knows. I don't think we can be expected to anticipate the long-range impact of quantum computing on the world. But based on the applications that we currently foresee, the most likely to have a substantial benefit for society are the applications to materials and chemistry, which can help to advance human health and energy production and agriculture and the sustainability of the planet. But it won't be easy. Building scalable quantum computers is one of the grand challenges facing 21st century science and technology. It's going to take a sustained effort and investment over decades to realize our aspirations for the field. But I think if we make that commitment, then we'll be amply rewarded in the end. Well, thank you for your attention.
Thank you so much, Professor Praskill, for your keynote speech. And also, we all benefited a lot from your lecture note, freely available on internet. And I don't think Professor John Praskill ever visited Korea. And this may be the first of his talk to Korean audience. And we move on to question and answer for the second session now.
Okay,
Andreas?
John, thank you very much for your very interesting talk. And if that is really true, if that is really true that you have never been to Korea, then I very, very highly invite you to come, and I will make sure that this happens in the next few years, right? So,
Thank you.
I particularly like the classification of quantumly easy. That's such a nice, catchy term. And you showed us that there are material science, chemistry kind of solutions that you know that are in that field. Maybe are there also more strictly business-related applications there, like optimization or search?
Well, we certainly hope so, but of the applications to optimization that we understand best, the speed up achieved by a quantum computer is not so spectacular, at least according to what we've so far been able to understand, as the speed ups achieved in simulations of quantum matter. But really, we still have a limited understanding of what that story is going to be. And I think what will make a difference is as the technology continues to advance, we'll be able to experiment more, and that will help us to discover and to perfect new applications.
Thank you. And maybe as a second question, let me put on a layman's head and ask you the very difficult question to explain to me as a layperson what is the real difference between a quantum computer and a classical computer?
Well, the way I would look at it is that, as others at this event have said, quantum physics is the fundamental theory of how matter behaves at a microscopic level, and that has been the basis of important technological innovations in the 20th century, like lasers and magnetic resonance imaging, and putting billions of transistors on a chip and so on. But those technologies don't really scratch the surface of how quantum physics has changed our perspective about what's possible in the physical world. Where new capabilities arise is when we have many quantum particles interacting with one another in a highly complex way. So we've used the word entanglement a few times today, and what's important about entanglement is that when many qubits become highly entangled with one another, there is such complexity in that system that we couldn't possibly hope to keep track of it with an ordinary classical computer. And that's where the big advantage of the quantum computer is coming from.
Great. Thank you very much.
I want to add just one short question. There's a so-called quantum annealing and a coherent Ising machine. They are not so quantum, not so classical. Do you have any comment on that?
Well, they're interesting technologies, and I think we have a limited understanding at this point of how powerful they are and the extent to which they can be scaled up to larger problems to realize a significant advantage over conventional computing. I think that's important to continue to explore. We need to experiment with those technologies to get a better grasp of their potential.
Now, this concludes the question and answer with Professor John Preskill. Thank you so much, Professor John Preskill.
Thank you.
Now, you are going to watch some special program. It is usually said that in quantum world, weird things are happening, something impossible in daily experience. The quantum world stimulates artistic imagination. Now, let's meet some artistic expression of quantum world.
The new artistic muse, the quantum. Today, quantum physics seems to be a popular muse for many artists. The truth is, this is not science and art's first meeting. The fusion of contemporary sciences and arts is a movement that has been ongoing since the 1990s. CERN, the world's largest particle physics laboratory, has been running an arts and culture program since 2011 called Arts at CERN, which annually supports artists who incorporate science into their creative activities. As such, Arts at CERN spoke of the union of quantum physics and art through their exhibit, Quantum Broken Symmetries. As of late, attempts to interpret art through quantum physics or render the discipline into an artistic subject have been actively made. Quantum Jungle by Robin Baumgarten. Liquid Reflection by Liliane Lian. Singlet and Multiplay by Jiyoung Kim and her team. Gap by Jiyoung Kim and her team. The quantum has become another muse of the artistic world. What do you think? We look forward to seeing more of the quantum and its artistic value in the future. Quantum physics in arts.
Now we are heading to the final session. Our final session focuses on the quantum technology startups and the future of quantum computing. And our last keynote speaker is Professor Jung-Sang Kim from Duke University. Professor Kim is the co-founder and chief technology officer of quantum computing service provider IonQ. He's also the fellow of the American Physical Society and Optica, as well as a senior member of IEEE. Professor Kim also serves as a founding member of the U.S. National Quantum Initiative Advisory Committee. He's with us online. Hello, Professor.
Hello.
Well, thank you for being with us today.
All right. Thank you for having me at this very interesting and exciting meeting. I was asked to talk about what is a startup environment like in quantum, and the really interesting thing is last summer when I counted, there are over 200 startup companies in the quantum realm in the world today, which I think is a very surprising event. When we started IonQ, there was probably the number of startups could be counted in your 10 fingers. So I think it's a really exciting development. Now, I would like to actually see, instead of getting deep into the technical details, I want to see, how technology evolves, looking at some of our more traditional computer as an example, and then point out what are the opportunities for technology firms, especially small startup companies like ours. So I'd like to start out by just looking at historical evolution of computing technology. And you see that the first invention of transistor was really a scientific endeavor. This was done at Bell Laboratories. It's actually, I was fortunate enough to have an office right next to where the first transistor was invented when I was working at Bell Labs. This was really a culmination of quantum physics that gave us an understanding of how electrons move inside semiconductors, really semiconductor physics, and then material science. And there was a lot of computational theory, as Professor Preskill indicated, just understanding of what problems are easy to solve with the computing machines and what are hard. Once the scientific foundation builds up, there actually is a phase where useful devices are built. And then there's this really interesting engineering process that pushes the performance of your systems up. It actually also increases the application space where computers can be useful. And then we actually see this exponentially growing economic value that's delivered by these new technologies. So this shows the example of a transistor density in semiconductor chips used in computers, dating back to somewhere in the late 1970s. And you can see that this large-scale integration very large-scale integration of VLSI technology allowed us to build more and more complex computer chips that can solve larger and larger problems at lower and lower cost. And then the adoption of this technology becomes extremely broad. And then that allows you to reinvest your value back into the technology so they can get to the next level and so on. So this engineering of so-called Moore's law is really not just a technology development, but it's really a law that indicates the value creation of this technology in our society. And as you go into this, not only the fabrication technology, but the architectures, how to build high-performance computers by aggregating very large numbers of computers together, and of course all the software ecosystem in building operating systems, the services and the applications and the distribution, all of that starts to influence how our lives are affected by this technology. Now, as the technology moves from science to engineering, and as it reaches more and more users, we come into a very interesting group of people called users. And here I'm showing a picture of a little kid doing their homework. And of course, for this person, how the computer works, how it's networked to the rest of the world where he or she can download information from the websites and so on. Exactly how that works is really of no interest. Right here, the value is how easy it is to use, what functions it can serve, so that he or she can do their homework or their learnings or play games or whatever the application is. So once the technology becomes real, it actually reaches millions, if not billions, of users who may have very little idea on how the technology works, but that focuses on the utility of what this technology can provide to you. So quantum computing, I think, has really started out in the scientific realm. It's actually making its way into the engineering domain. As Professor Preskill indicated, many of us believe that the impact of this will be very large. And then the next step is, what is the first application where quantum computing can actually deliver some real value against the classical computers? Because that is the foundation on which more usefulness of this actually builds over time. So the first interesting note for the users is how do we get to useful quantum computers, and how are we going to measure that? In the early stage of technology development, it is the technology drivers who tend to put out metrics and performance indicators. And in the early days, we did ask questions like the transistor density, or how many transistors in your quantum computers or smartphone has, and what is the clock speed of your processor, and things like that. But one of the interesting indicators of recognition is that some of these device-level metrics don't necessarily translate to what a user can do with a computer. And as the industry matures and the users who are less familiar with the technology start to think about how to use them, we very quickly move to application-based benchmarks. And this is tests for representative use cases. So, for example, if I'm interested in playing a game with my computer, I'm interested in the refresh rate of the video screens and how expressive the video screens are, and that those kinds of things become very interesting and important to me. Whereas if I'm doing scientific applications, the amount of data you can put in, the number crunching you can do becomes more interesting. So there are thousands and thousands of different uses of a classical computer. And we actually create benchmarks that measure the performance of your machine against some of these use cases. And that actually gives the users a real indicator of what type of computer they should use and what kind of performance metrics they should look for. And in a similar way, there has been similar efforts in quantum computing. There is an industry consortium called Quantum Economic Development Consortium, which have come together and thought about, some of the useful quantum algorithms that we can use to measure the performance of quantum computers. So this shows an example of what IonQ's quantum computers can do. And here we actually, this is a fairly complex plot, but in a typical quantum algorithm, you have some number of qubits that you want to use to solve or execute on your algorithms, and then you actually have some depth of the circuit. Some quantum algorithms are relatively short. Other quantum algorithms can be very long, and it really, because quantum computer gates, the logic gates that we use to the computation is not perfect. If the circuit becomes very, very deep and long, then today's NISQ quantum computers tend to have a lot of trouble executing those machines. So we actually measure both quantum circuit width, which is how many qubits you can actually deploy in your computation, and also the number of entangling gate operations that represent the depth of the circuit. Also is a metric of how good of a high performance gates you can perform with this. And then you actually measure its performance by running these representative algorithms. And here we show 6 algorithms that are pretty widely used in a typical quantum computer. And we actually execute these circuits and say, okay, what is the success probability? The quantum computer will give you a correct answer to that problem of that size. So, for example, and then we actually allocate a metric called algorithmic qubits, where if you have an algorithmic qubits of say 20, that means you can use 20 qubits in your quantum computer, and you can run entangling a circuit that contains on the order of 400 entangling gates among them. And then you can run many applications of interest, typically specified by a list, and to make sure that you get a pretty reasonable success probability when these algorithms are executed. So this actually gives you a measure of how powerful your quantum computer becomes against the problems that you're interested in. And it allows you to measure that and keep track of it. And for a hardware technology developer like ourselves, it gives you a goal of improving the utility to the user. So we are actually focusing on this utility as a metric by which we communicate with our users. All right, so what is some of the future holds on quantum computers? The opportunities of quantum computing, exactly where it will be the killer application will show up, is something that I think is still ahead of us. We have some new early applications we have to find out what new early applications are enabled by quantum computers. Now, if you take a reference to some of the early applications for disruptive technologies, the first applications where they become extremely useful are not necessarily the one that you thought was going to be the most useful. For example, when transistors were first developed, they were used as amplifiers. And back in those days, the amplifiers were used to transmit signals on telephone lines over long distances. But it turned out that the first real interesting application was a hearing aid. That's because transistors can now amplify signals with very low power dissipation and very slow turnover latency. So now you can actually have amplifiers that can actually be operated on a battery. And hearing aid and transistor radios were the first applications that drove the transistor technology. When you think about solid-state memories, that's in your laptop computers and iPads all day, the first applications was not in computers. They were in digital cameras and iPods, the MP3 players. In digital cameras, the concept existed for some time, but were not practical until solid-state memories came by. And initially, the capacity of solid-state memories was so small that using them on computer systems was not very practical. But once the applications like digital cameras came by, then it made a perfect sense to use those new storage media. And over time, the capacity and the cost improved so dramatically. And today, they replace your entire hard disk drives and solids in your laptops. And for the internet, when the internet first came about, there were very few computers that had a need to exchange the largest amounts of data. And it actually really started its application in scientific data sharing for high-energy physicists. What we really need to focus on is enable development of new approaches to solve new problems and difficult problems that people thought were not attackable before. And that we have learned that quantum computers can tackle better than traditional. There are problems that quantum computers can tackle better than traditional computers. And in order to do that, we actually have to get to a regime where quantum computers' capability has to exceed supercomputers. Or you can actually do the same kind of computations either better, cheaper, or faster than supercomputers. So a technology company like ours, we have a meticulous focus on making sure that we build quantum computers with that kind of performance using the utility metric that we introduced earlier in the presentation. And then once you do that, then you have to make it easy to use and accessible. So you think about App Store. Many people don't know how to build iPhones, but the Apple has provided an application store where people add the development tools so that you can create your applications and deploy it and reach millions of users at the same time. So what this means is if we make quantum computers powerful enough, but also create a platform for people to come in and innovate, then you can think about lots and lots of interesting applications that most of us scientists don't think about that will be enabled by quantum computers. So I think that's the really exciting feature. Startup companies can actually create, grab some corner of this ecosystem that we're going to be building and have an explosive growth as the opportunities actually grow with it. With that, I'd like to conclude and take any questions. Thank you.
Thank you so much, Professor Jung-Sang Kim. You gave a very inspiring talk, and due to lack of time, we have to skip questions. Thank you so much.
Thank you.
Now, this concludes the Q&A session with Professor Jung-Sang Kim.
Okay, it's about time to wrap up, actually, hold a session. So, Professor Kim, what do you think about today's forum?
Yeah, when I was a student, I thought that quantum mechanics is always behind the curtain, not showing up in front. Now we are suddenly face to face with the smiling face of quantum computers and many other quantum information applications. I hope that this forum encourages many young Korean students to cope with the quantum challenge in their future.
Okay, we conclude today's forum with closing remarks by GSI Director Sun Hoon. Without his enthusiasm, interest, and initiative, this forum would not have been possible. Before we go, I'd like to send gratitude to distinguished speakers, excellent guests, and wonderful viewers. Thank you so much.
Yes, I'd like to thank all the speakers and panelists and also two hosts for organizing and participating in this forum. And also special thanks to all the STEM members who made it possible. We try to make this forum as easy as possible for general public, but I'm not sure how successful it was. But hopefully this forum provided some insights for quantum technology. And also, as I mentioned at the beginning, we are preparing 2 additional forums later this year. One will be on how science and technology can minimize social inequality and division. And also the second one will be renewable technology. So I hope that you can also join us for these 2 forums. And you can find more information regarding these 2 forums from our website at gsi.kaist.ac.kr. With all that, I'd like to thank the audience for watching this forum, and now the session is adjourned. Thank you.